Today we are going to discuss the structure of metals and alloys. Here a metal is an elemental substance and an alloy is a homogeneous mixture of two or more metals or a metal and a non-metal. Among the solid materials, metals and alloys predominate because of their characteristics of hardness, strength, rigidity, formability, machinability, weldability, conductivity and dimensional stability. All elements can exist as either solid, liquid or gases depending upon the condition of temperature and pressure. The term solid is nothing but it is a state of matter in which the substance possesses rigidity and tendency to maintain both its shape and volume. Substance can be classified as amorphous or crystalline. As mentioned in introduction, substance is classified as amorphous or crystalline. Let us see what is amorphous and crystalline. Amorphous is nothing but if the elementary particles are mixed together in a disorderly manner, their positions bearing no fixed relationship to those of their neighbors. Whereas crystalline, in a crystalline material, the arrangement of atoms is in a periodically repeating pattern. A crystalline solid can be either a single crystal or an aggregate of many crystals. Now let us see what are the topics to be covered in the session. Now we are going to cover about effect of rate of cooling on grain size, effect of grain size on mechanical properties, factors promoting grain size, phenomenon of crystallization and space lattice, unit cell and also important parts of structures of lattice, etc. Now let us know about the space lattice. Space lattice is nothing but it is defined as atoms of metal are arranged in orderly pattern which results in a geometric shape called a crystal lattice or a space lattice. Let us see how space lattice can be shown. Here you see this is a space lattice. The atoms are orderly arranged in cubic cell. Space lattice contains number of cubic or unit cells. See, in every corner there are atoms arranged in orderly manner. See, you can see here there is a unit cell. Here the unit cell is in three axes, say x, y and z. In the space lattice, the unit cell are arranged according to the axis and also grows equally according to the axis. Here you see a angle between the x and z axis is the alpha, angle between the z and y axis is the beta, and angle between the y and x is the alpha. Now let us see how unit cell is defined. Here you can see unit cell, that is the smallest unit having the full symmetry of crystal is called unit cell. Now you see another figure clearly, that is unit cell. See, these are the lines constructed according showing the cube. See B, this is B, this is C, this is A. Between B and C angle is alpha, and between C and A angle is beta, and between A and B angle is gamma. Here in unit cell at all the corners the atoms are arranged in orderly. Here the dimensions of the sides are A is equal to B and is equal to C. Now angles also equal to 90 degrees, that is alpha equal to beta and beta equal to gamma, which is equal to 90 degrees. Now these unit cells can be divided into two types, that is, unit cell may be primitive or non-primitive. Now let us see what is primitive and what is non-primitive. Here the primitive is, it is constructed in a cubic, that is A equal to B, B equal to C and C equal to A, and angles are alpha equal to beta equal to gamma, which is equal to 90 degrees. Now the atoms are arranged themselves in the cube at the corners. We can see the arrangement of the atoms. Here in the four corners the atoms are arranged. Then this type of cell is called as primitive unit cell. Now let us see non-primitive unit cell. Here this is also similar to the unit cell. The difference is, here the atoms also arranged in interior parts of the cube and also faces of the cube. Then this type of cell is called as non-primitive unit cell. There are 14 types of space lattices. Let us see those types. One is simple cubic, second one is body centered cubic, that is can be denoted as BCC, and third one is face centered cubic, that is FCC, and another cubic is hexagonal close packed lattice, and another one is simple tetragonal, and next one is body centered tetragonal lattices. Sixth one is simple orthorhombic, now base centered orthorhombic, and another one is face centered orthorhombic, body centered orthorhombic, and another one is simple monoclinic and base centered monoclinic, and the other one is triclinic. These are the number of types of space lattices, but in these types of space lattices only 4 space lattices are stable in most of the metallic structures. Let us see those space lattices. Now you can see simple cubic space lattice. Here there is a cube and which contains atoms arranged themselves at the corners. You can see this view, these are the 4 atoms arranged at the corners. Now you see the angle between the sides, that is A to B is gamma and B to C is alpha and C to A is beta. The alpha is equal to beta is equal to gamma, that is equal to 90 degrees. Then you can see body centered cubic lattice. It is most of the similar to the simple cubic lattice, but the difference of the lattice is this: in the cubic center atom is arranged. You can see the atom, that is center atom arranged, that is why we can say body centered cubic lattice. Now you can see face centered cubic lattice. In the face centered cubic lattice all the 6 faces have 6 atoms. See, now you can see it is similar to the simple cubic lattice. Now let us arrange the other 6 atoms on the faces of the cube. Now see, these are the 6 atoms arranged on the faces of the lattice. That's why it is called as face centered cubic lattice. Now let us see the other type of lattice, that is tetragonal lattice, that is simple tetragonal lattice. In simple tetragonal lattice, the A is equal to B, but B is not equal to C and C is not equal to A. But here the angles between B and C and A and B is equal to 90 degrees. But this type of lattice not existed in most of the metallic structure. Now you can see another type, that is same tetragonal group. This is body centered tetragonal lattice. Here in this lattice an atom is arranged by themselves in the center of the body. That is why it is called as body centered tetragonal lattice. Now let us see orthorhombic lattices. These are simple orthorhombic, body centered orthorhombic, base centered orthorhombic and face centered orthorhombic. Here the dimensions of the cube is A is not equal to B and also B is not equal to C and also C is not equal to A. Then the angles, but the angles are alpha is equal to beta, beta is equal to gamma, which is equal to 90 degrees. Here in simple orthorhombic only 4 atoms are arranged at the corners. In body centered orthorhombic only center atom is arranged including the atoms arranged in the corners, that is body centered orthorhombic. Now base centered orthorhombic, in the base centered orthorhombic only on the basis of the structure having atoms. This is one atom on one base, this is another base, another atom. The remaining atoms are arranged at the corners. Similarly, in face centered orthorhombic the atoms are arranged on faces of the structure including the atoms at the corners of the structure. Now let us see monoclinic lattice. Here these are two types, simple monoclinic and the another one is base centered monoclinic. Here it is also the sides of the structure is not equal, that is A is not equal to B, B is not equal to C and also C is not equal to A, but the angle between alpha is equal to gamma is 90 degrees, but which is not equal to beta. Now you can see another type of lattice, that is triclinic. Here in this lattice only the atoms are arranged in the corners of the structure. The dimensions of the structure is A is not equal to B, B is not equal to C, but also angles not alpha not equal to beta, beta not equal to gamma and gamma is not equal to 90 degrees. Now you see another type, rhombohedral type lattice. Here you can see the structure is looking like a rhombus. So then that's why it is called as rhombohedral lattice. Here the sides of the rhombohedral is equal, that is A is equal to B, B is equal to C, but the angle alpha is equal to beta, beta is equal to gamma, but which are not equal to 90 degrees. Now let us see what is the packing factor. This packing factor is used to calculate the density of the material. So let us know what is packing factor. It is defined as the ratio of the volume of the atoms per unit cell and to the total volume occupied by the unit cell. Now you see mathematical equation of the packing factor. Packing factor is equal to volume of the unit cell by total volume of the unit cell. The definition part of the atomic packing factor we have discussed now. Let us solve a problem to find out the atomic packing factor. Here you can see how to compute the packing factor for FCC. You see the problem, compute atomic packing factor for FCC. FCC is face centered cubic lattice. We know atomic packing factor is the ratio of volume of atoms per unit cell to the volume of the unit cell. We are denoting volume of the atoms per unit cell is small v, volume of the unit cell is bigger V. But we know effective number of atoms in face centered cubic is 4. Now volume of 4 atoms is equal to 4 multiplied by volume of sphere, because the atom is in spherical shape. Here the diameter of the atom is equal to 2r, this is 1/6 part of the atom, that is equal to r, this is also r. Now the atomic radius for face centered cubic lattice is equal to a into root 2 by 4, but volume of sphere is 4 by 3 into pi into r cube. Here where a is the side of the unit cell and r is atomic radius. Now volume of atoms per unit cell V is equal to 4 into 4 by 3 pi r cube. This 4 by 3 pi r cube is substituted in the place of volume of sphere. Now you simplify this. By simplifying this one, 4 into 4 will be 16 by 3 into pi, that is into a root 2 by 4 to the power of cube. Now this is equal to pi into a cube into root 2 by 6. As we know, volume of the unit cell, that is capital V, is equal to a cube. Atomic packing factor is equal to small v by bigger V. This is equal to pi into a cube into root 2 by 6 into 1 by a cube. Here a cube and a cube is cancelled. After simplifying this value, you get the 0.74. Like this, we are finding atomic packing factor for FCC. Now let us discuss about the important metallic structures. Those are body centered cubic structure, or we can also call it as body centered cubic lattice. Now you can see the view. Here there are 4 atoms arranged at the corners. In middle you can see a blue color atom which is arranged in the center of the body. Here this by seeing this cube, we can clearly show the atoms in the corners and also another atom at the center of the body. The examples of the body centered cubic lattice for a metal is chromium, vanadium, molybdenum, manganese and alpha iron. Now let us see the effective atoms of the BCC structure. Here see, these are the atoms arranged in the corners. This is the center atom. You see in the diagram B. Here this part, you can see this part is 1/8 of the atom. So this 1/8 is taken in all the corners. Therefore 8 atoms shares at the corner. Therefore 8 atoms into 1/8 is equal to 1 atom, and there is one center atom. This is the center atom, that is also which is equal to 1 atom. Now total effective atoms arranged in body centered cubic is 2 atoms. Now packing factor of the body centered cubic is 0.68. Now let us see another type of lattice. This is face centered cubic structure. Now you can see the atoms are arranged on faces of the cubic along with the atoms arranged in the corners of the cube. Now you can see the clear picture of FCC. Here there are atoms arranged in the corners. Now you see the atoms arranged on the faces of the body centered cubic. You see these are the atoms arranged on the faces of the structure. Now let us know some examples for face centered cubic. One is copper, silver, gold, aluminum, lead, iron, this is gamma iron, beta chromium, beta cobalt and nickel and platinum. These are the metals having face centered cubic structure. Now let us see effective number of atoms in the face centered cubic structure. Now you see the diagram, the atoms are arranged on the faces of the cube and also arranged in the corners of the cube. Now here this part is 1/8 of an atom. In 8 corners, 8 atoms shares at the corners, that is 1/8, that is equal to 1 atom, and on 6 face centered atoms, on each face sharing by 1 atom, that is 6 face centered atoms into 1 by 2, that is equal to 3 atoms. Now total atoms in the face centered cubic structure is 4 atoms. Now packing factor of the face centered cubic structure is 0.74. Now let us see hexagonal close packed lattice. Here the structure is in hexagonal shape. On the hexagonal faces, in all 6 corners there are 6 atoms are arranged, and on face of the hexagonal is arranged 1 atom, and similarly on the another base 6 atoms arranged in the corners, and center atom is on the face of the base. Now another 3 atoms are arranged in triangular shape. This is arranged in the in between the triangle of this atom and this atom and this atom, and similarly leaving this triangle, in another triangle another atom is arranged in center of this triangle, and similarly by leaving one triangle shape it is taking another triangle and there is another atom arranged. Like that in the structure there are 3 atoms arranged. Now let us see examples for hexagonal close packed structure. Now see, the beryllium is the hexagonal close packed structure, magnesium also, zinc, cadmium, alpha, cobalt. These are the metals are in a hexagonal close packed structure. Now let us see the effective number of atoms in the hexagonal close packed structure. Here you see the diagram, these are all the atoms 1, 2, 3, 4, 5, 6. This is 6 atoms in the corners of the face of the hexagonal, and there is another center atom, and middle in triangular shape there are 3 atoms, and on bottom base this is another 6 atoms arranged in the corners. Here you can see how the atoms are shared in the corners. Here there are 12 atoms shares at the corner in the 1/6 part. Now 12 atoms into 1/6 will give the 2 atoms, and 2 atoms at the 2 hexagonal faces which are shared by 2 faces. This is one and this is another. Therefore 2 into 1 by 2 will give the 1 atom. 3 center atoms will give the 3 atoms. Now total effective number of atoms in the hexagonal close packed is, there are 2 plus 1 plus 3, and this is equal to 6 atoms. Now let us see packing factor of the hexagonal close packed structure. See, packing factor is 0.74. Substance as classified as amorphous or crystalline. Amorphous is nothing but if the elementary particles are mixed together in a disorderly manner, their positions bearing no fixed relationship to those of their neighbors. Whereas crystalline, in a crystalline material the arrangement of atoms is in a periodically repeating pattern. A crystalline solid can be either a single crystal or an aggregate of many crystals. Space lattice is nothing but it is defined as atoms of metal are arranged in orderly pattern which results in a geometric shape called a crystal lattice or a space lattice. Unit cell, that is the smallest unit having the full symmetry of crystal is called unit cell. Unit cell may be primitive or non-primitive. There are 14 types of space lattices. Let us see those types. One is simple cubic, second one is body centered cubic, that is can be denoted as BCC, and third one is face centered cubic, that is FCC, and another cubic is hexagonal close packed lattice, and another one is simple tetragonal, and next one is body centered tetragonal lattices. Simple orthorhombic, now base centered orthorhombic, and another one is face centered orthorhombic, body centered orthorhombic, and another one is simple monoclinic and base centered monoclinic, and the other one is triclinic. These are the number of types of space lattices. What is packing factor? It is defined as the ratio of the volume of the atoms per unit cell and to the total volume occupied by the unit cell. Packing factor is equal to volume of the unit cell by total volume of the unit cell. Examples of the body centered cubic lattice for a metal is chromium, vanadium, molybdenum, manganese, and alpha iron. Total effective atoms arranged in body centered cubic is 2 atoms. Packing factor of the body centered cubic is 0.68. Some examples for face centered cubic. One is copper, silver, gold, aluminum, lead, iron, this is gamma iron, beta chromium, beta cobalt, and nickel and platinum. Total atoms in the face centered cubic structure is 4 atoms. Now packing factor of the face centered cubic structure is 0.74. The examples for hexagonal close packed structure. Now see, the beryllium is the hexagonal close packed structure, magnesium also, zinc, cadmium, alpha, cobalt. Now total effective number of atoms in the hexagonal close packed is 6 atoms. The packing factor is 0.74. Now, in this session we have discussed the crystal, that is orderly array of atoms in space, and space lattice. It is a 3-dimensional network of imaginary lines connecting the atoms in a repetitive crystal structure in space, and also unit cell. It is the smallest unit having the full symmetry of a crystal. Types of space lattices. Most of the engineering metals crystallize either in cubic or hexagonal systems. With this, we are closing the session. Thank you.
Further clarification, contact the Additional Secretary, State Board of Technical Education and Training, 7th floor, BRKR Bhavan, Tank Bund Road, Hyderabad 500063. Fax 040 322 0546.